We're going to talk about board setup. Board setup is all about the physical constraints for manufacturing, and it also is other critical things like how many layers of copper are there in the board, how close can copper elements be. So jump over to this menu, Edit Board Setup, and let's take a look at it. We're not going to cover everything exhaustively, just the things that I think are the most critical. In the physical stack up menu, this is where we can change how many copper layers we have. So if I make this 4, then we'll have 2 outer layers and 2 inner layers. This isn't used just to get you out of like routing problems because you can have more copper traces penetrating through the board, but it's also used for impedance control boards, like high speed boards where those inner layers create very well controlled transmission lines. So you might want to explore with the impedance controlled checkbox as well. But in a 4-layer board, you'll notice our right-hand menu now has the front copper, the back copper, which we're used to toggling between with V, but now we have in 1 and in 2, and we can increment to the next layer with the plus key or decrement with the minus key. So if we were to lay a trace on the front copper, then we can click, click, click. We're used to jumping to the back layer with V, and I'll strike H to go into high contrast mode. So now we're on the back layer, and if I press minus, we'll jump to the in2 inner layer, and if I press minus again, we'll jump to the in1 inner layer. So you can see as I toggle through these layers, things can get pretty complex pretty quickly. So why might you want a multi-layer board? They're quite a bit more expensive in general, but you can do things like impedance controlled traces. So if you have like a high-speed USB line, or if you just need to separate all those signals. Usually in a 4-layer board, it's the outer layers that are heaviest in copper. So you often have power layers on the outside and the inner layers are for signal. I'll return that to 2 layers and we'll move along. Board finish, not that important. Solder mask, this is more for setting like manufacturer level recommendations. It's usually fine to leave this as 0. You may find when you're generating Gerbers that you get hit with a warning, and that might be prompting you that you've moved away from defaults in this window, or you should put in the manufacturer's constraints into this window. We'll look at manufacturers in a sec. Text and graphic, this is all just, default art styles really. Now we get to the design rule section, which is where things get interesting. These constraints are really the absolute cannot be violated constraints. When you're routing your traces or placing your parts, KiCad will not allow you to break these constraints. And so we see with things like minimum clearance, this is the minimum distance between copper items that are not on the same net. And this is 0 by default because we're just using the defaults for our net classes. In general, KiCad's defaults are pretty conservative and will work with most manufacturers. You'll get a manufacturable board if you use the default clearances. Here's a very accessible board manufacturer, JLC PCB, and every board manufacturer will have a capabilities section where you can click that capabilities and just look at what's possible with their manufacturing process. All the way from very gross things like board dimensions, materials. When we start getting down into more constraint areas like drill sizes, plated through-hole sizes, the pad size, the minimum annular ring for how big the copper ring needs to be around a through-hole, plated slots. But when we come down to, say, minimum trace and width spacing, here we have the minimum spacing between traces as 0.127 and the minimum trace width as also 0.127. This is for a 1 to 2 layer board. So if you needed to use a part that demanded smaller clearances than that, then you might need to go to a multi-layer board because they're often built with higher tolerances. But it's really helpful to know because it's heartbreaking to design a board and then get to the manufacturer and have them spank you because you broke one of their rules. A classic one is things like copper to edge clearance, where our manufacturer has a hard limit of 0.3 millimeters. So here's that trace to the routed edge. So if you wanted to be very frugal, you could put that 0.3 millimeters in as a hard constraint. KiCad's pretty conservative though, so it's probably fine. Now, as I was writing this board, I made a bit of a mistake. I was putting in these nice, big, thick 0.4 millimeter traces for power, and that was coming from our capacitor. But the trace between the regulator and the capacitor is this weedy little 0.25 millimeter trace. And that's just because I wasn't paying attention. If I had taken the time to set up a net class, I could have avoided this problem. Now, when we're laying traces, by default, the track uses the net class width. And I created a custom width of 0.4 millimeters and just started using that for my power lines. It would have been more scalable if I had made that net class. So I go into settings, and under net classes, I can add a new net class called high current. And these are all the default properties, but I really care about the width. I know that clearance is going to be fine, but this is mostly just a standard track where I want to have a bit of extra width. We've created our high current net class, and now we need to assign some nets to that class, and that's in this window down below. We can create a new pattern, and the net that we're interested in is the plus 5V net, the plus 5 volt. There it is. I guess we really want the plus 5 and the plus 12. So everything that carries high, because this is going to carry the same current, because this is a linear regulator. If I'm drawing an amp out of it, it's going to be drawing an amp into it. So I wonder if I can put in a wildcard. Great. So we have our plus 12V and our plus 5V nets. And of course, we want to assign that pattern to the high current net class. And click OK. Great, so we've assigned the net class. Nothing's changed on our board though, because we had already routed some traces. There are a couple of things we could do. I could select that trace and strike E, then check to use net class width, and it'll blow up to that 0.4. I could press U to select the whole thing and delete, U and delete, and now when I press X and route, that should default to that 0.4 millimeter net class width. And I've just undone those changes so I can show you the last variant, which is to go to Edit, Edit Track and Via Properties. And here we can select Filter Items by Net Class High Current, because we want to push this change to every track that happens to be on the high current net class. And we can just force them to update to those net class values if they aren't already. I'm doing it for tracks and vias. And so when I click OK, we should see these balloon up to the new width. And there they go. Of course, be careful doing this, because now that all your traces have widened, you may be violating some DRC constraints. Now, I wouldn't just go blanket updating the width of traces willy-nilly, especially since when that happens, your new trace widths may be in violation of DRC constraints. So when you run that DRC again, you might have your work cut out for you, but it's still a really handy tool to have in the back pocket. And so there you go. Every time I pick up off one of these power nets, I get a thick trace, but if I pick up off any other net, I get that thin trace. That is very handy.